Hey there, Seahawks. It's Miss Adams, and in this video, we're going to talk about probability and probability rules. Alrighty, so experimental probability and theoretical probability. Experimental probability is the actual probability of an outcome in an experiment. So if I toss a coin 30 times and get 12 heads, what is the experimental probability of getting heads? So 12 out of 30 would be 40. The theoretical probability is the expected probability of an outcome. All right, so if we're dealing with flipping a coin, I would expect it to be 50% of the time heads. The law of large numbers is like one of the main laws that we talk about in statistics, is as the number of trials increases, the experimental probability should get closer to the theoretical probability. All right, so if we're doing the coin example and I ran a simulation for 10 trials, maybe I had 7 heads, 100 trials, maybe I had 44 heads, 500 trials, maybe I had 233, and 1,000, I got 492 out of 1,000. So you can see like the percentage as I do more trials is getting closer and closer to the theoretical probability of 50%. All right, your sample space is the list of all possible outcomes. What is the sample space when rolling 2 dice? This depends on what we are measuring. So could be numbers 2 through 12, or all the different combinations per roll, so like a 1 and a 1, a 2 and a 1, a 3 and a 1, etc. The notation that we're using for probability. So A, B, C, we use these capital letters a lot of times. Those are our events. Capital P and then in parentheses A is the probability of event A happening. S is our sample space. And A with a little C exponent is the complement of A, which means not A. You can also see it with like a prime, like a little dash mark. 3 probability rules that you need to be aware of. So all probabilities must be a value between 0 and 100%, or between 0 and 1 if I'm not writing them in percentage form. The probability of S, which is my sample space, is always going to be equal to 1 or 100%. So all of my outcomes have to add up to 100%. And the probability of A complement is equal to 1 minus the probability of A. So the probability of an event not happening is equal to 1 minus the probability of it happening. All right, your turn. If the probability of hitting a home run is 30%, what is the probability of not hitting a home run? All right, probability of a home run is 30%. Not a home run would be 1 minus 30%, which is 70%. If there are only 8 different blood types, fill in the chart below. Again, we said all of the probabilities have to add up to 100. The ones I have here add up to 0.94 or 94%. So 1 minus 0.94 gives me 0.06 or 6%. Gambler Jack, when asked to predict the ACC basketball championship, follows a modern practice of giving probabilistic predictions. He says UNC's probability of winning is twice Duke's. NC State and UVA each have probability of 0.1 of winning, but Duke's probability is 3 times that. Nobody else has a chance. Has Jack given a legitimate assignment of probabilities to all teams in this conference? Why or why not? So let's figure out what exactly he gave probabilities. So he said NC State was 0.1 and UVA was 0.1. Duke was 3 times that, so 0.3. And UNC was 2 times Duke, which is 2 times 0.3, so 0.6. All right, so we know that all probabilities have to add up to 1, but if I add these, I actually get 1.1, so no good. All right. All right, union and intersection. Union, the meaning is representing the outcomes in event A or event B or both. All right, so we use this U symbol. I like to think of that as uniting them together, and we would read it as or. The intersection is, we read it as and. It's representing the outcomes that are in both events A and event B. So what they have in common, and we use the symbol where it kind of goes up. All right, I kind of remember it as like it's the N in the word and the other one, U, kind of looks like the letter U for union or unite. All right, Venn diagrams. Use shapes to represent events. The box around the shape represents the sample space, so everything has to be within that box. All right, the probability of A is 0.26, the probability of B is 0.41, the probability of A and B is 0.1. Draw the diagram. So you really need to start with that centerpiece where they're overlapping. The probability of A and B is 0.1. Well, the probability of A is 0.26, but part of that is already being accounted for in the center, so I have to not count that part twice. So the rest of A is 0.16. B is 0.41, and again, part of it's already accounted for, so the rest of B is 0.31. They have to add up to one whole, and so the remaining is 0.43. All right, another example. The probability of A is 0.32, probability of B is 0.61, probability of A and B is 0.22. So I'm going to fill in my Venn diagram. So 0.22 is going to go in that center, the A and B. The rest of A would be 0.1, the rest of B would be 0.39, and the rest of my sample space would be 0.29. Now, the probability of A or B, so it can be A, it can be in B, or both. Right? So that would be 0.71. And so some people like to kind of like highlight, so it could be an A or B or both, and then add up all the sections that they highlighted if you're more of a visual person. The probability of not A or B. So not A would be all of this, or B means I can take anything in B. So it's everything but the 0.1, so it would be 0.9. The probability of not A or not B. So it's not A, which would be all of this stuff, or not B, which would be all of this stuff. So it's everything but that centerpiece, so 0.78. The probability of not A and B, so it's not in A and it's in B, which would be 0.39. The probability of not A and not B would be the 0.29 that's in the sample space. That's not within A and B. All right, your turn. Real estate ad suggests that 23% of homes for sale have fireplaces, 65% have a second bathroom, and 13% have both features. What is the probability that the home for sale has? Go ahead and try. All right, so if you're filling in the Venn diagram, you have 13% in the middle. For fireplace, the rest is 0.1. For bathroom, the rest is 0.52. And the remaining is 0.25. So a second bathroom and a fireplace. So that would be B and F, which is the overlapping section. So 0.13. Neither a second bathroom nor a fireplace, so it'd be not B and not C, and not F, excuse me, which would be the 0.25. All right, a second bathroom but no fireplace. So that would be a second bathroom, but it can't have a fireplace. So that would just be 0.52. All right, probability rules with union. So our general rule, this is on the reference sheet that you'll get for your AP exam. The probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. So for a deck of cards, when picking one card, what is the probability of picking a red card or a face card? All right, so the probability of red or face. So half of the cards are reds, 26 out of 52 cards. Plus 12 out of the 52 cards are face cards, king, queen, or jack, and there's 4 suits. All right, minus there are 6 face cards that are red. Okay, I don't want to count those face cards, those red face cards, twice. I don't want to count them in the reds and count them in the face cards. So I have them right now counting for both. So I have to subtract them one time so that they're not being doubly counted. And that gives me 32 out of 52. Special cases. What if A and B don't overlap? So the probability of A and B equals 0. Okay, so you can see that those circles are not overlapping. We can call that disjoint or mutually exclusive. So picking a red card and a spade. All right, their red spades are not red. So the probability of that happening is 0. 2 events are disjoint if they have no outcomes in common. All right, so disjoint events, if you have disjoint events, the probability of A or B is just the probability of A plus the probability of B, because the probability of A and B equals 0. All right, we are picking one card out of a standard 52 card deck. What is the probability of picking a heart or a spade? So, heart or spade. So, hearts, I have 13 out of the 52 cards are hearts. And same for spades. I have 13 out of 52 are spades. I do not have any hearts that are also spades. So, it's either a heart or a spade. It cannot be both. So, that just gives me 26 out of 52. A 3 or a spade. So, I have 4 threes in a deck out of 52 cards. I have 13 spades. And I have one 3 of spades. So that's going to give me 16 out of 52 cards. A queen or a king. Well, I have 4 queens and 4 kings in a deck. I cannot be a queen and a king at the same time. So that is 8 out of 52. A red card or a heart. So half of my cards are red. So 26 out of 52. Plus hearts, I have 13 out of 52. Minus hearts are red. All hearts are red. So minus 13 out of 52, which just leaves me with 26 out of 52. A black card or a face card. So half of my cards are black, so 26 out of 52. Plus I have 12 face cards. Of those 12 face cards, 6 of them are black face cards, so minus 6 out of 52 gives me 32 out of 52. And when you're working with probabilities, you can keep them fractions, decimals, percentage. You can simplify or not simplify. The AP exam is not super picky on this. So your turn. The probability of event G is 0.25 and event K is 0.34. The probability of G and K is 0.1. What is the probability of G or K? All right, so we're using our rules. Probability of G or K is the probability of G plus the probability of K minus the probability of G and K. All right, so 0.25 plus 0.34 minus 0.1 gives me 0.49. All right, intersections and conditional probabilities. So conditional probability is the probability of A given B, and we use that vertical line there. So that is the probability of event A happening given that event B happened already. This is also on your reference sheet. So the probability of A given B is equal to the probability of A and B divided by the probability of B. So the one that comes after that vertical line, whatever piece that is, that's always going to be your denominator. All right, so I can use this working backwards if I want to find the probability of A and B. So it'd be the probability of A given B times the probability of B. All right, independence. If you're rolling a die, flipping a coin, picking things with replacement, that means you're taking them out, putting them back in, then those events are events that would be independent. If the probability of A given B equals the probability of A, then events A and B are independent. For independent events, the probability of A and B is also equal to the probability of A times the probability of B. All right, these two formulas are not on your reference sheet, and these are definitely something you're going to want to have stored in the memory banks because it will show up on the AP exam. All right, this example, the probability of J is 0.23, the probability of B is 0.67, the probability of J given B is 0.15. What is the probability of J and B? Alrighty, so the probability of J and B is equal to the probability of J and B divided by the probability of B. That's the formula for conditional probability. I'm going to fill in the pieces I know. So 0.15 equals, I don't know this, over the probability of B is 0.67. I want to get that numerator, so I'm going to multiply both sides by that denominator of 0.67, and I get 0.1005. Are J and B independent? Well, the probability of J and B has to be equal to the probability of J times the probability of B. That's one way to check for independence. Or the probability of J given B has to be equal to the probability of J. So those are our two methods for checking for independence. I'm going to go ahead and fill in what I know. So I just found the probability of J and B was 0.1005. The probability of J times the probability of B is 0.1541. So those are not independent. If I use the other method, the probability of J given B is 0.15. The probability of J is 0.23. Those are not independent. Are J and B disjoint? All right. So in order to be disjoint, that means that the probability of J and B would have to be equal to 0. But we just found that the probability of J and B was not equal to 0. It was equal to 10.05%. So, no, they are not disjoint. All right, this example, go ahead and try it. All right, what is the probability of A given C? So it's A and C divided by the probability of C, which would give you 0.5641. What is the probability of C given A? So this would be A and C divided by the probability of A. Again, remember that piece after the vertical line is your denominator. That would give you 0.4889. Are C and A independent? So no, if you do the conditional probability equal to the probability of A, they are not. There are other methods you could have used to check. Are they disjoint? No, the probability of A and C is not equal to 0. All right, use the following table about grade level and favorite type of pet to answer the probability questions. If someone is a sophomore, what is the probability they like dogs the most? So, probability they like dogs given they're a sophomore. So this is out of the group of sophomores. So, out of the group of sophomores, 18 of them like dogs. Out of the group of sophomores, out of 43 total sophomores. So, 0.4186. Given that someone likes cats, that means out of the group that like cats, what is the probability they are a junior? So, probability of junior given cats would be I had 13 juniors like cats out of 47 total people that liked cats, so 0.2766. We pick a freshman at random. What is the probability they like other the most? So, other, given they are a freshman. So, 12 freshmen picked other out of 34 total freshmen. So, 0.3529. In a bag of gummy bears, 12 were red, 8 were green, 9 were orange, and 10 were yellow. Find the probability that you eat a red bear, then a green bear. So, red first, then green. So, red and green. So red was, there were 12 red out of 39 total gummy bears. Well, if I ate the red one, now there's 38. And I didn't eat any of the green, so I still have 8 green left. Okay, so 0.065. Eat a red bear and a green bear. So red and green. 12 out of 39 times 8 out of 38. Again, same basic concept here. But I could also have done it the other way around, right? So I could have done the green first, so 8 out of 39 plus 12 out of 38. So there's two different possibilities for how this could have happened. So I have to add those two possibilities, right? So there's a greater chance that this could have happened than the first outcome. Like you have to eat red first, then green. This one's just saying a red and a green. All right, the next one, eat 3 orange bears. All right, so orange and orange and orange. So at first there was 9 oranges out of 39 total. Then there was only 8 oranges out of 38 total. Then there was only 7 oranges out of 37 total. All right. All right, your turn. Go ahead and pause and try this. Suppose 40% of cars in your area are manufactured in the U.S., 30% in Japan, 10% in Germany, and 20% in other countries. If cars are selected at random, find the probability that a car is not U.S. made. All right, so I went ahead and put together all of these probabilities here. So the probability it's not U.S. would be 1 minus probability it is U.S. It's made in Japan or Germany. So Japan or Germany. Again, it can't be made in both, so there is no overlap. So I'm just adding those probabilities. You see 2 in a row from Japan. So Japan and Japan, which should be 0.3 times 0.3. Okay, I'm assuming this is a large enough sample that I don't have to worry about, like, well, now there's 1 less possibility from Japan, right? None of the 3 cars came from Germany, so not Germany and not Germany and not Germany. Well, Germany was 10%, so 90% would be not Germany 3 times, so 0.729. At least 1 of 3 cars is U.S. made, so at least 1. Whenever you see at least 1, it's going to be 1 minus the probability of none. So at least 1 is 1 minus the probability of none. So I'm going to find the probability that none of them were U.S. made. And then I'm going to subtract that from 1 so that I can find the probability that at least 1 of them was U.S. made. Right? So not US made would be 0.6. 3 of them would be 0.6 to the third. Find that probability, subtract it from 1, I get 0.784. The first Japanese car is the fourth one you choose. Okay, so it'd be not Japanese, not Japanese, not Japanese, and then Japanese. Which is 0.7 times 0.7 times 0.7 times 0.3, which is 0.1029. All right. At a local track meet, 62% of participants were girls, 29% of the participants were from private school, and 18% of participants were girls from private schools. What is the probability that a randomly selected student was a girl or from a private school? All right, so we know that 62% were girls, 29% were from private school, and 18% were girl and private school. So girl or private school would be 0.62 plus 0.29 minus 0.18, which is 0.73. What is the probability that a randomly selected girl was from a private school? So private school, given they are a girl, is both, so the and piece divided by the probability that they're a girl, which is 0.2903. What is the probability that a randomly selected public school student was a girl? All right, so I am assuming these are independent events. So I assumed independence to find the probability of girl and not private or not private school. So that gave me 0.44 over 0.71, which is 0.6197. Is being a girl and being from private school mutually exclusive? So no, in order to be mutually exclusive, again, that would have to equal 0. Is being a girl and being from private school independent? All right. Yes. So the probability of private school given they are a girl would be equal to the probability of private school. Well, private school given they're a girl, I found as 0.2903, which is equal to the probability of the from private school, which is 0.29. Okay. Sometimes they're not going to be exact, but they're going to be pretty close. All right, tree diagrams. An airline offers discounted tickets to customers who buy tickets early, more than 30 days. The company has noticed that 60% of its tickets, that its customers take advantage of early bird fares, while 25% purchase regular fares and 15% are last-minute customers, less than 48 hours. They have also figured out that the no-show rate among early bird purchases is 30% and only 8% among regular fare customers, 2% among last-minute customers. Create a tree diagram for this situation. All right, so I have 3 possibilities. They either purchase a ticket early, regular, or late, and then they either are a no-show or they show to that flight. All right, so these are kind of my branches. So I know that 60% of customers purchase early, 25% regular, and 15% late. Of those that purchase early, 30% are no-shows, which means 70% do show. Of those that purchase regular, 8% are no-show, which means 92% show. Of those that purchase late, 2% are no-shows, which means 98 are showing. And then I'm going to multiply across that branch. So 0.6 times 0.3 is 0.18, 0.6 times 0.7 is 0.42, and so on. All right, so I get all of these probabilities. And then when I'm multiplying across, that's the probability it's early and a no-show. Early and a show. Regular and a no-show. Alrighty. What is the probability of being a no-show overall? So I'm taking all of those no-show probabilities and adding them together. All right, so all of the ones that were no-show, that included no-show, and adding those final branches. What is the probability of being a no-show and a last-minute customer? So a no-show and a last-minute customer is 0.003. Given that you have a no-show in a certain seat, what is the probability that the person being a last-minute customer? So last-minute, given they were a no-show, so it'd be last-minute and no-show divided by no-show. So divide those two probabilities I just found, I get 0.0148. Given that you have a no-show in a certain seat, what is the probability of that person being a regular fare customer? So regular given no-show. Regular and no-show divided by no-show. So 0.02 divided by 0.203, which is 0.0985. Given that you have a person show up for a certain seat, what is the probability that person's an early bird customer? So early bird given they show up. So early bird and show up divided by the probability they show up. I'm going to divide those and I get 0.527. So if you have a lot of questions on probability, I really like making a tree diagram. Sometimes it's a little bit more work if you only have like one or two simple questions. But I prefer tree diagrams. I know not everybody does. All right, there are two textbook making companies, A and B. It is known that 1% of company A's books are defective. It is known that 2% of company B's books are defective. Sun Lake High School gets 38% of its books from company A and the rest from company B. Make a tree diagram below, then answer the questions. All right, so I'm either going to order books from company A or B. They're either going to be defective or not defective. So again, that little C as the exponent means not that. It's the complement. All right, so A, we get 38% of our books from company A, which means 62% come from company B. From company A, 1% of the books are defective, so 99 are not. Company B, 2% are defective, so 98 are not. I'm going to multiply across my branches, and I get these probabilities. So the probability it comes from company A and it's defective is 0.38%, and so on. All right. What is the probability that a book is not defective? So again, I'm adding up the not defectives. If a book is not defective, what is the probability that it came from company B? All right, so this came from company B given it was not defective. So that would be come from company B and not defective divided by the probability it's not defective, which I get 0.6176. If we open a book and it is defective, what is the probability that it's from company A and then it's from company B? So the probability it's from A given it's defective. I'm also going to find the probability it's from company B given it's defective. All right, so these are the two probabilities I get. All right, your turn. See if you can try this one. A VCR manufacturer receives 70% of its parts from factory A and the rest from factory B. Suppose 3% of the output from A are defective, while 2% of the output from B are defective. So we're going to make our tree diagram. Okay. Then I'm going to use that to answer some questions. What is the probability that a received part is defective? So the probability it's defective, I'm adding up all the defective parts. If a randomly chosen part is defective, what is the probability it came from factory A? So A given it's defective, and then B given it's defective. All right, I hope that you tried that one and you got those answers correct. All right, try this one. A particular football team is known to run 30% of its plays to the left and 70% to the right. A linebacker on an opposing team notes that the right guard shifts his stance more of the time, 80%, when players go to the right, and that he uses a balanced stance the rest of the time. When players go left, the guard takes a balanced stance 90% of the time, and the shift stance the remaining 10%. What is the probability that the player will go to the left if the guard is balanced? All right, so he's either going to go left or right. He's either going to have a shifted stance or a balanced stance. All right, so 30% of the time they go left, 70% of the time they go right. Of the times that they go left, he has a balanced stance 90% of the time. When he goes right, he has a shifted stance 80% of the time. All right, multiply across, and we can use this to answer our question. So the probability that they go left, given it's a balanced stance, so left and balanced divided by the probability of balanced. So it would be 0.27, which is left and balanced, divided by the total for balance, which is 0.27 plus 0.14, which is 0.41, which gives me 0.6585. All right, go Seahawks.